Hello everyone, I am Ankur Haldar and welcome back to my channel Mind Over Matter, and this is the first lecture of the lecture series called From High School to Physics. And in this lecture I will be talking about sets. You can guess that pretty well from the title of this lecture, Understanding Sets. And so before I start, I want to give a free advice that when you are doing problems in physics and mathematics, and you have to take your emotions aside from the equations, and the only expression that you should be worrying about is the definition. Okay, so by saying that, I would like to state at first the definition of a set, and then I will build the concepts over it. Okay, so what is a set? Okay, let me select the pencil. Yep. So what is a set? A set is a collection of distinct objects. Okay, so it's basically a collection. It's nothing, there's nothing fancy in it. Okay, so suppose I have collected some numbers. I have collected 1 3, I have collected 1000, I have collected 2024. So with these four numbers, I can make a set out of it, and by giving curly brackets, I'm saying that these four elements form a set. Suppose I am naming it set A. Okay, so the each entry inside a set is called an element or an object. Element or object. Okay, so each entry is an element or an object of the set, and in this particular set there are four elements: 1 3 1000 and 2024. And it's not necessary that the elements are numbers, so I can form a set with some letters also. Suppose B, Z and X. I am forming a set with these letters. Okay, so here the elements are alphabets, and yeah, so this is also a set. I can also form a set with words, like suppose I am making a set of some fruits: apple, banana, what else is there, apple, banana and strawberry. So this is also a set with three elements: apple, banana and strawberry. And also you have to remember that a set can also contain another set. So there can be a set D whose elements are set A, set B and set C. Okay, so there's nothing to worry about as long as the elements are well defined. Okay, as long as the elements are well defined, you can form a set out of it. So yeah, so that's the thing. Now I would like to show you the form of sets. Okay, a set can be written in two forms. The forms I was writing here were the roster form. Let me give you an example. Suppose there is a set E called it has four elements: 2 4 6 and 8. Okay, so this is the roster form. And this same set can be written like this: the set E is X, such that this sign is such that X is all the even integers between 1 and 10. Okay, so yeah, this form is called the set builder form. They basically are the same set. In the first form, in the roster form, you have to write the elements explicitly. Okay, but in the set builder form, you just have you just have to write the one symbol, and you have to mention what's the logic behind the elements. Okay, so here's the logic: is that the elements are all the even integers between 1 and 10. Okay, so x belongs to all the even integers between 1 and 10. Okay, another thing that I would like to say that a set is a collection of distinct objects. This word is very important, distinct. What does that mean? It means that the elements are unique. Okay, so let me give you an example. You can have a set like this 1, 2 and 3, but you cannot have a set like this 1, 2, 2, 3, 3, 3. Okay, so no, this cannot happen because one element cannot repeat. An element can repeat only once in a set. Okay, so that's why the elements have to be distinct. These are not distinct elements, these are the same elements. So a same element cannot occur twice in a set. Okay, so this is the rule. And also the ordering of the elements does not matter whether you write 1, 2 or 3, or you write 2, 3 or 1. It doesn't matter. They as our definition doesn't say anything about ordering, so the ordering doesn't matter. So these two are basically the same sets, 1, 2 and 3, and 2, 3 and 1. Okay, so let's continue from this, and I will be stating some standard set notations. And at first I would like to say that the set of all natural numbers. Okay, the set of all natural numbers can be written like this: 1, 2, 3, 4, 5, dot, 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 dot. And there are infinite natural numbers, so it's impossible to write all of them. And excuse me, this set is naturally denoted in the literature by the letter capital N with a bold 2 lines in between the parallel lines of N. Okay, so it's written like that, and there's nothing fancy, it's just a notation, nothing else. So again, another set is set of all integers. A set of all integers, it contains all the natural numbers, it contains 0 as well, and it also contains all the negative numbers, negative integers. Okay, all the negative integers. So naturally we write it with the letter capital Z. And there is another set, the set of all rational numbers. So if you don't know what a rational number is, I think it will be best if you look in your textbook, in some high school textbook. There is definition of rational number, but I'm going to mention it again. Okay, so set of all rational numbers is denoted by the letter Q, and it is all the elements A over B such that A and B both belongs to integers. Okay, and B is not equal to 0. Okay, yeah, so B is not equal to 0. So this sign is called belongs to. Belongs to means that A and B are both elements of Z, the integer, the set of all integers that I have just written. And B cannot be 0. As you can see, we cannot divide anything with 0. So if there is a 0 here in the place of B, then it's undefined. Actually, it's not rational anymore. So this is the set of all rational numbers, and now I will be writing the set of all the real numbers. So this is denoted by the letter R, and it actually contains all rational and irrational numbers. So all integers are also rational because there's the denominator is 1, and all the fractions are also rational, or they're irrational. They can be both of them. They're either rational or irrational. Okay, they cannot be both of them at the same time, but they can be rational or irrational. All rational and irrational numbers. Irrational numbers are the numbers that cannot be written like this form, A by B. Okay, all rational and irrational numbers. Such irrational numbers example is pi, root over 2, root over 3, etc. So yeah. and this is the set of all real numbers. And now let's come to the final one, the set of all the complex numbers. If you don't know anything about complex numbers, do not worry, I will be covering complex numbers in a later video in this very playlist. Yeah, so this is denoted by the capital letter C, and this is all the elements of the form a plus ib, such that a and b both are real and I is basically root over minus 1. If you don't know anything about complex numbers, then do not worry, I will be explaining complex numbers explicitly in a later video. And one thing that you can notice here, that if we set b equal to 0, then it's basically the set of all complex numbers becomes the set of all real numbers. So from this analogy we can draw a diagram. Suppose this is the set of all complex numbers, and if we set b equal to 0, then there's another small set of all the real numbers in it. Okay, so all real numbers are complex numbers, but all complex numbers are not real numbers. Okay, and if we exclude all the irrational numbers from real numbers, then yeah, we have all the set of all rational numbers q. So yeah, and if we exclude all the fractions from rational number, and then we get all the integers z, and if we exclude all the negative integers and 0, then we get the set of natural numbers. Okay, the set of natural numbers. So from this we can say that the set of all complex numbers is a bigger set, and set of all real numbers is not as big as complex number, because all real numbers are complex numbers. Okay, and this concept, this diagram and the concept will be will come handy when I'll be explaining the concept of subsets very soon. Okay, let's continue first, then we will comment about subsets. Okay, so now we are going to talk about types of sets. Let me change the color. Okay, types of sets. Types of sets. So number 1 is finite set. Finite set is nothing but a set which has a finite number of elements. It's absolutely simple. Finite numbers, finite number of elements. Example, suppose we have a set which is 1 2 3. It's a finite 1 2 3. It's a finite set. And also suppose we have the set of all the vowels a, e, I, o and u. So this is also a finite set, because both of them has limited or countable finite number of elements. Here it is 3 and here it is 5. And another type is, you can guess it from it's infinite set. So basically it has infinite number of elements. Can you guess what an infinite set can be? A number of elements. Yeah, we have just learned about infinite sets. Wait a minute. So all the sets that I was talking about before, n, and set of all integers, set of all real numbers, set of all rational numbers, set of all complex numbers, they are all infinite set. Okay, so yeah, they are all infinite set. Another example that I can give you, suppose a is x such that x belongs to natural number. So yeah, x is natural number and x is greater than, suppose, 10. So yeah, this set, this is a set builder form. In roster form this looks like this: 11, 12, 13, and it goes on and on and on and on to infinity. Okay, so this is the concept of finite set and infinite set. Let me continue to the second one. The second type of set is a singleton set. A singleton set. What is a singleton set? It has only one element. So if a set has only one element, then we can call it a singleton set. Suppose we have A is 100. So this is a singleton set because it has only one element, and we can also give examples in alphabet. Suppose B is Z. So this is not the set of all integers Z. This is the English alphabet Z. Okay. So this is also a singleton set. And another type of set is the null set. A null set has nothing in it. Okay. It has no elements. So if it has nothing in it, so it's basically written like this. There are only the curly brackets, but there's nothing in between them. So there is no elements actually in a null set, and we generally denote this with the letter Greek or Latin. I cannot recall the letter phi. I think it's Greek, okay, with the Greek letter phi. And one thing that people commonly mistake that a null set is this, but a set which contains 0, it's not a null set, it's a singleton set, it's not a null set. Okay, because it has the element 0, right? Even if a set contains the null set itself, then also the whole set is not a null set, it's a singleton set. Okay, so this is like this. So a set contains the null set, but that means that it has an element, right? It has an element which is a null set, and that's completely okay, but it doesn't mean that the whole set is a null set. Okay, so this is also singleton set. And another thing is equal sets. If A and B have the same elements, then they are equal sets. Same elements, then they are equal sets. Okay, so a very simple example. Suppose A is 2, 4 and 8, and B is 8, 2 and 4. So yeah, they both have the same elements. They both have 2, they both have 4, they both have 8. So yeah, they are same. So we can denote with them with equal to, A equal to B. Okay, and now a very important concept comes in, is the concept of subsets. Okay, subsets. What is a subset? Suppose A is a subset of B if all the elements in A are present in B. So we generally denote it with this sign. This is a subset sign. And well, let me give you an example. Suppose B is 1. Oh, okay, just a minute, I made a mistake. Yeah, curly brackets. I gave first bracket. No, it's curly bracket. B is 1, 2, 3, 4. Okay, so all the subsets B can have a subset, like suppose A is 1 and 2. Okay, so yeah, A is a subset of B because 1 and 2 both are present in B. And also if another set is 2, 3 and 4, so yeah, C is also a subset of B. And if another set is the B set itself, 1, 2, 3, 4, then also D is a subset of B, because look, the definition says if all the elements are present in B, then it's a subset. Look, it's 1, 2, and 3 and 4, so they all are present in B. So D is a subset of B, okay, according to the definition. And also another important thing, that phi, which has nothing in it, is also a subset of B. Okay, so grasp this concept. Phi has nothing in it, so you don't have to worry about the elements in it being in B or not. So it has totally nothing in it. So B can have phi in what can I say? B can have nothing in it without you know, without altering 1, 2, 3, and 4. So B has nothing but 1, 2, 3, and 4. So phi is also a subset of B. Okay, so as phi has nothing in it, so nothing, you know, we cannot express this in words, but I think you are getting the feeling. So if you are not getting the feeling, then please feel free to contact me. We will have a special discussion on this concept. And yeah, phi is basically a subset, of every set. Yeah, subset phi is, or the null set is subset of every set. This is a very important concept. Just with the same analogy I used here, so phi is subset of every set. Sorry, I forgot to write the word set. Okay, and another thing called proper subset. What is proper subset? A is a proper subset of B. So this sign is proper subset if A is not equal to B. So in our previous example, here A is also a proper subset of B. C is also a proper subset of B. Phi is also a proper subset of B. But D is not a proper subset of B. D is a subset of B. Okay. Yeah. So this is the definition of a proper subset. And now we come to another important concept called universal set. Universal set. And before getting into universal sets, I would like to give an example. Suppose you are at your home and you give a statement that you have to cook dinner tonight, and then what are the ingredients that you have? What will be the planning that comes in your mind? You have oil, you have food in refrigerator, you have oven, you have salts, the spices, the stove, and everything. And so basically you have all the required equipments you need to make a dinner. But think about the same statement but said in a different position. Now suppose you are stranded alone in an island, and you are saying that I have to cook my dinner tonight. So there the scenario is drastically different. So you have suppose you have a spear, you have to catch some fishes with it, you have some sticks, you have to build a fire, and you have to burn the fish and eat. So that's the definition of dinner there. So basically in both the scenarios you have different universes with you. So that means you have different options, you have different ingredients with you. So that's why you have to think differently. All the work you have to do they all has to be within the given equipments that you have. So we can say that in both the cases, the universal set of cooking your dinner, universal set of the equipments of cooking dinner is different. Okay. So basically a universal set contains all the elements. All elements, yeah. And suppose we are talking about natural numbers, then the universal set will be our set of all natural numbers. Suppose we are talking about integers, then we are dealing with integers, then our universal set will be integers, and just like that. And remember one thing, that every set is a subset of the universal set. the universal set. Okay, so that's how universal set is defined. So every set has to be a subset of the universal set. So universal set must contain all the elements. Okay, now we are going to talk about a little different topic. We are going to talk about some operations on set. Okay, let me take another color. This is good. Operations on sets. Okay, number one, it's called union. Suppose I have a set A, that's 1, 2 and 3, and I have another set B, 2, 3, 4 and 5. Then I can make another set called A union B, and that actually contains all the elements in A and B without repeating. Okay, so yeah, it contains 1 because 1 is in A, it contains 2 because it is in A, and it's also in B, but we cannot repeat the same element twice because elements of a set must be distinct, that we mentioned in the first definition in today's lecture. Okay, and it also has 3, 4 and 5. Okay, so this is the operation union. Union means that all the A union B contains all the possible elements in A and B. And using Venn diagrams, we can actually make this a bit simpler. So what is a Venn diagram? It's nothing but just a way to picture the sets. Okay, here we picture the sets with circles. Okay, so suppose this is my set A, and every element of set A is present inside this circle. And suppose this is my set B. These are the elements that present in B. And look here, the region inside both A and B, that means this region, there are 3 elements here also. So we will talk about that in intersection part, but now let's call about union. Let's talk about union. So A union B is all the elements in A and B together. Okay, so it's all the area of the 2 circles. Okay, so I think you have understood it now. Okay, and so nextly I would like to talk about intersection. Yeah, intersection. With the same example, A is 1, 2 and 3 and B is 2, 3, 4 and 5. So A intersection B, this is the sign of intersection. A intersection B only contains the elements that are present in both A and B. So in this particular case, 2 is present in both A and B and 3 is present in both A and B. So A intersection B is basically this set 2 and 3. Yeah, so using Venn diagrams we can also picture this. Suppose this is my set A and this is my set B, and this area is the A intersection B part, because this area is present in both A circle and B circle, right? Okay, so next up we have difference. It's a very important thing, difference. And yeah, difference, and we will use the same example again. A is 1, 2 and 3 and B is 2, 3, 4 and 5. Okay, so basically A difference B means that all the elements of A will be present in this set, but they should not be in B. Okay, the elements which are only in A, they will be present in A difference B. Okay, so there's only one element in A that's not in B. That is 1. So this will be the A difference B, the set of A difference B. And similarly, you can see that B difference A, it is the set that contains all the elements in B that are not present, that are not present in A. Yeah. So 4 and 5 are such two elements. They are present in B but not in A. Okay. And using Venn diagrams again, suppose this is my set A and this is my set B, and this portion is actually the part where the elements are only a part of A, but they are not present in B. So this part is A difference B. And similarly, you can also picture B minus A. So this part is B minus A, because this part is only a part of the B circle. It's not a part of A circle. Okay, I think this is enough for difference. And now let's go to another concept called the complement. Complement. Yeah. So suppose we have a universal set 1, 2, 3, 4, and 5, and we have a set A that contains 1 and 2. Remember that all the as we have set our universal set as 1, 2, 3, 4, and 5, and all the sets that we are going to talk about under this problem must be a subset of this universal set. That means that it cannot contain any other elements than 1, 2, 3, 4, 5, and yeah, so it cannot contain any other sets than 1, 2, 3, 4, and 5. So A is suppose A is a set 1 and 2. The elements of A are 1 and 2, and A complement is the set which it is basically the elements which are present in the universal set but not in A. Okay, so in this case it is 3, 4, and 5. So you can say that it is U difference A. Yeah, it's the same. So using Venn diagram, suppose this is my U, this rectangle, and this is my A, and this portion that is not present in A is my A complement. Okay, yeah. So now let's talk about another topic called the power set. It's a very easy thing. If you have understood all the concepts I have been talking about, then yeah, power set is a very easy thing. So suppose we have a set called A, and it has elements 1 and 2. Then the power set of A, sorry, what did I write? The power set of A contains all the possible subsets of A. Okay, so you can guess that one possible subset of A is the set which contains 1, the set which contains 2 is also a subset, the A itself is a subset of A, and also the null set or the phi. Sorry, I mistakenly okay, so this is the power set of A. So a power set of another set A contains all the possible subsets of A. So yeah, that's the power set. And yeah, there's another thing, another theorem, that if there's a set, if A is a set that contains, if A contains n elements, then power set of A must contain two to the power n elements. we can verify this theorem in our example. So here we had a set, we had set A, and that had two elements, and according to our theorem the power set must have 2 to the power n. In this case n is 2, so 2 to the power 2, that is 4 elements. The power set of A must have 4 elements. So yeah, it has 4 elements. These 4 elements are the elements of power set. So yeah, this is a very important theorem, and it can come handy at several times, but yeah. So I cannot recall any particular case where this theorem comes handy, but yeah, it can be useful sometime. Okay, now we are going to talk about another important topic called the Cartesian product. So let me change the color again. This is very important. Pay attention. And the Cartesian product. If suppose there are two sets A and B, then their Cartesian product is denoted by this sign of multiplication, or cross, A cross B. It is basically all the elements inside a first bracket. So in this case, this is an element, the whole thing, this is an element. Okay, this is the element, not A is not an element, B is not an element, but whole A comma B is one single element. Okay, it contains this element such that small a belongs to set A and small b belongs to set capital B. Yeah, okay, yeah. So this is the definition of Cartesian product. Let me give you an example. Suppose we have A is 1 and 2, and we have B x and y. So A cross B will be all the elements which has the first element, all the elements, or you can say these are the tuples. You can say these are the tuples as elements. You don't have to worry about the word tuple. Okay, so every element has two elements taken from A and B, the first one from A, the second one from B. Okay, so this can be an element of A cross B, 1 comma x, because 1 comes from A and x comes from B. Okay, similarly 1 comma y, 2 comma x, and 2 comma y. So these are the elements of Cartesian product of A and B. But remember, x comma 2 cannot be, it cannot be an element of A cross B. So this sign means that does not belongs to. Okay, so this cannot be an element of A cross B, because here the first element comes from B set. So A cross B must have the tuples where the first elements are from A set. But x comma 2 can be, it can belong to B cross A, right? So let me write down it. B cross A is nothing but simply the first element of every tuple will come from B and the second one will come from A. So it's just the reverse of A cross B. It will be x comma 1, y comma 1, x comma 2, and y comma 2. Okay, so this is the concept of Cartesian product. And yeah, this concept will come very important. You will see in the next lecture. The next lecture is about relations, and we will see that Cartesian product will be very important there, because we will define our relations using Cartesian product. So if you did not understand Cartesian product, then please rewind the video and rewatch this portion again. And if you still do not understand, then please feel free to contact me. I will give you some lecture notes that I have prepared, some lecture notes that I will be providing that. Yeah, my contact details will be there in the description box. And so yeah, I also have some, yeah, I have covered all of the topics, and I also have some practice problems and exercises. There are 4 problems. If you are interested, then please contact me through my email or WhatsApp. I think I will be putting both in the description, and also I'll be putting the my LinkedIn profile there, and you can go and have a chat with me there. So yeah, these are all the things that I I talked about today. So let's make a summary. We first learned about the definition of sets, and secondly we came to know about types of sets. Thirdly we understood what are the operations on sets. And fourthly we understood what is a power set. And fifth, the important part was Cartesian product of two sets. It's also an operation, okay, but as it is a little it's a little complex, so I did not include it in portion 3. Okay, so we also learned about Cartesian product. So Cartesian product will be very important for the next video, and I highly recommend you to watch this video again and again until you have cleared the concepts and the basics of set theory. And yeah, so I will be I will see you next time on the next video. And yeah, so bye bye.